Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I was last time, where I started talking about asymptotic notations. Last time I gave you a bunch of different definitions. I gave you a definition for big O, big omega, big theta, and I also talked about a couple of variants like little o and little omega. I'm going to be mostly focusing on those first three in this lecture. So I thought I would do some examples with you today, proving big O claims, big omega claims, and big theta claims. I also was showing you some properties of big O and big theta and all the other families here. So that's what the plan is. So I'm going to really just be going boom, 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 boom through a bunch of examples. So I'm going to be trying to touch on a lot of things today. So hopefully I'm not going to be going too fast for you today. So I thought I would start off with something a little bit more elementary, just to make sure everybody's sort of on the same footing when it comes to this big O stuff and this formal definition. So I just want to remind you of the game plan. So I like to call like the idea for which you prove the claim a game plan, because I find it's a little bit easier to follow when you know, okay, that's really what we need to do. So I wanted to remind you of the formal definition of big O. So remember, F is big O of G if and only if there exist these two constants, C and N0, such that this inequality holds for all n greater or equal to N0. So there's the game plan is quite simple. You have to show me this constant and this constant. You want to show me the C and the N0. But it's not just about showing them to me. You have to demonstrate mathematically, that dreaded M word, that these two constants actually work. So when you show me this inequality here, this inequality has to hold for all n greater or equal to N0. So very often what we'll do when we try to prove these claims is we'll show some observation that is generally a well-established fact about something, and we'll use that to get to the goal. So the strategy I like to use is I like to pick one of the constants and then use that information to get the other constant. This isn't obvious. You could do this in several different ways, but I find with a lot of the claims that you'll encounter, it's very often that C will be the thing you first pick, and then you try to find N0. There's a lot of other ways you could do this as well. I'm not going to be touching on so-called root solving. You may have seen that in 210, where you have two curves or two functions, and you try to find the intersection of the two curves, and you find out, oh, well, n is everything onto the right side of the curve when it crosses. Instead, I'm going to be focusing more on something more formal. So I'll be building more on your ability to communicate in rigorous terms how something is true, as opposed to using more just basic algebra. So there's a few tips I have. First, you want to remember, you want to go from one point to the next. It's not about explaining to me why the claim is true. It's about giving me an argument. So I start at one thing, I tell you what I'm going to do, I do something as a result of that, and then I tell you what I'm going to do with that information. The next thing is that if I give you some inequality, I have to quantify it. So for example, if I tell you, oh, n is less than or equal to something, I have to tell you for what n that's true or false, or if I'm even showing you that that is true or false. There may be a case that I'm just writing something down just to demonstrate it's true or false, or I may even say that the inequality is false. So don't just blindly write down an inequality. You have to quantify it with something around it using words or some quantifier, like over here where I say this inequality holds for all n greater or equal to N0. So these are just some general tips I'm giving you here, because it's very easy to fall into any one of these traps. So the first thing I want to do is I want to do this example. 5n squared plus n is big O of n squared. Now, I want to give you some intuition of how I can prove this. So there's many ways you can prove this, but I'm going to try to show you the simplest way I can think of to do this. And I'm going to show you a standard trick to doing this for anything that looks like this. So the first thing I want you to think about is, okay, I would like to have it so that everything on this side looks kind of like this. So my goal is I want to show this inequality holds, right? But I want to try to use C to make something that looks like this. It doesn't have to be equal to it, but it has to look kind of like it. So that I can argue that the left-hand side is less than or equal to the right-hand side for all n greater or equal to n0. And ideally, in this kind of situation, I would try to make n0 equal to 1, which is the smallest possible value you could give n0. So let me just start us off here. So first I describe what I'm going to do. So we need to find constants C, which is a positive real number, and n0, which is a positive integer. That's what that plus means on this fancy blackboard Z, such that for all n greater or equal to n0, I want to plug in f and g. Remember, this is f, that's g. 5n squared plus n is less than or equal to cn squared. Now, I want to give you some motivation behind what I'm going to do next, because this is where the big observation is going to happen. I'm going to pick c first, and then once I have c, I'm going to try to figure out what n0 can be. There's many ways you could do this. Sometimes you might do some algebra right about here where you try to simplify that inequality. So you remember, when you do that, you have to make sure you say, okay, well, we're trying to find the n0 in the c such that this holds. And then you can say, well, this is something else, and that you can simplify it using algebra, right? You don't have, like, you could say, oh, I'm going to divide both sides by n or something like that. You could say something like that. It's pretty straightforward. Or you could say this if and only if this, for all n greater or equal to n0, and so on and so on. But I want to start really basic here. So I have a couple bins here. And what I'm going to do is I'm going to try to think about this as, this is the left side of that inequality. That's the 5n squared plus n. This is the right side of that inequality. Okay, so I know that if I wanted to make this look something like this, I would need to have, so I have 5n squared here, and then I have some n here. I would like to pretend that this n is an n squared, because you'll see when I do that, the rationale is, okay, if I have 5n squareds on one side, so right now I have 5 of them, I have 5n squareds in this one bucket. And I make it look like an n, so if I make that n over there, I have to think of it like an n squared. Now I have 6 objects in my bucket. What I would like to do is I would like to match that on the right-hand side. I want to make sure I put 6 things in this bucket as well. So if I have 6 in this one, and I have 6 in this other bin, if both of them have 6 items in there, you would agree with me that this is less than or equal to this, right? If I think about them in terms of the number of bottles I have in these 2 bins, right? So that's going to be the intuition I'm going to use. I'm going to try to make this be at least this by pretending that any term that's a lower order term, so for example, this is n squared, that's n. If I pretend that this is actually n squared here, I can count them up. And if I think about it like that, an ideal choice for C might be, let's see, I got 5 of these, and look how many bottles did I have in here? I had 6, right? So I'm going to pick 6. So I'm going to try picking 6 as C. So I pick C is equal to 6, then we need, that's supposed to say 2. I need to find n0 so that for all n greater or equal to n0, that's a little bit crumped in there, for all n greater or equal to n0, that 5n squared plus n is less than or equal to c is 6, right? 6 times n squared. Now this is where I'm going to, yeah, see, perfect. So what I'm going to do is now I'm going to basically try to write out what I just said with these 2 buckets. So I'm going to write this out by taking each one of the terms, because now watch. Now I want you to walk back with me to what I did just before. So remember, if I have 6 on one side, I apologize for any noise coming from the fun capsules. Okay. So you'd agree with me that there's 5n squared on this side, and then there's 6n squared on that side, right? So you'd agree with me that I could expand out this 6n squared to be 5n squared plus n squared, right? So I could compare the 5n squared against another 5n squared, right? So I notice that I have 5 on one side, 5 on the other side. Now, remember, I want to pretend that the n is this n squared. So you'd agree with me that 5n squared is less or equal to 5n squared for all n greater or equal to 1, because they're in fact equal to one another, right? So next, what I'm going to do is I'm just going to pretend that that n is in fact an n squared. But remember, it is still an n, but it's at least n squared, right? So now if I have 6 on one side and 6 on the other side, you'd agree with me that everything on the left side is less than or equal to what's on the right-hand side. That's essentially what we're going to write out in this next statement. All I'm going to do is compare each one of the terms here against something in terms of n squared. That's all I'm going to do. So there's no magic tricks. It's just I'm going to use this idea of comparing each term, because when I sum over all of these terms, the inequalities have to hold when I sum over those inequalities. So notice that 5n squared plus n is less than or equal to 5n squared plus n squared, which is of course equal to 6n squared. Now remember, 6 is c. Now this is where we have to be careful. I have to justify for you why this is true. So I say for all n greater or equal to 1, that's the quantifier. So this is me saying that this is going to be true for all n greater or equal to 1. And here's the justification. As, like I said before, as 5n squared is less than or equal to 5n squared for all n greater or equal to 1, and n is less than or equal to n squared for all n greater or equal to 1. So you can see when I take these two inequalities, I have 5n squared is less or equal to 5n squared, and I have n is less or equal to n squared. By the way, if you're wanting to justify why this is true, just divide both sides by n, then you'll end up with n is greater or equal to 1. You can do the same thing with any one of these inequalities when you have this trick that I'm using here. It's not magic, it's just a bit of reasoning. But notice that if I look at this one, and I add everything on the left side, so these two right here, that's my 6 on one side. If I add these two, I get my 6n squared on the other side. So all I'm doing is I'm actually really just summing over inequalities. And when you do that, you sum everything on the left side, and you sum everything on the right side of the inequalities. And since each one holds, the sum over all the inequalities has to be true. That's all I'm doing here. Isn't that neat? So notice I'm not pulling out anything fancy-pantsy algebraically to really do this. So can somebody tell me what should I pick for n0 then? What should I pick for n0? Now keep in mind there's many values for n0 that work. But which one would work? Like, yeah, I see 1 in the chat. Yeah, 1 is perfect, right? See, all these inequalities work when n is greater or equal to 1. So I just gotta pick 1. Remember, I can't pick 0 because n0 has to be a positive integer. So choose n0 is equal to 1. Therefore, so now I have my c and n0, and I've justified both of them. So I can say, therefore, by the definition of big O, 5n squared plus n is big O of n squared, and we're done. Boom. Isn't that nice? It's not too bad at all. So the big thing is I've also included a conclusion that tells me how I'm using these constants, right? Because this is the part that connects me finding these two constants together, right? Because that's what's in the definition up here. Does everybody understand the pieces? So I tell you what I'm going to do. I figure out c and n0. I justify them for you using some sort of argument. And then I give a conclusion that wraps everything in a bow by invoking the definition of big O. Isn't that nice? So let me proceed. I want to show you that this, what I just described, this thing with the bins, this bin approach that I just used is actually something that's far more general than just thinking about, oh, I have two terms, I make one look like the other one. There's actually a far more general way of thinking about this. I've included the full proof for this in the notes. So I'd recommend you take a read of that. And you'll notice that exactly what I just described, where I divide both sides by the largest polynomial term and so on, that all pops up in this proof. So I want to talk about polynomials, so just general polynomials. So I'm not talking about just 5n squared plus n. I'm talking about, oh yeah, no. Like if there is like, this is a polynomial where I have coefficients a1, a2, all the way up to ak. And I'm going to multiply each one of these terms, starting at n raised to the power of k, n raised to the power of k minus 1, all the way down. If you really want to see it, there's the end of the power 0 right there. So you can write polynomials like I have on that side in terms of this one by setting certain coefficients here into being 0 and assuming k is some integer constant. So just as an example, the previous one I have over there, 5n squared plus n, I could just simply have k is equal to 2, and I can have it so that a0 is equal to 5, and I can have a1 be equal to 1, and I can have a2 equal to 0. I'll let you think about how that can be used to write out a polynomial out of this form. So notice that whenever I put a 0 in, that means that that term in the polynomial doesn't exist. Now I must also stress that there is a way to easily generalize what I have here to also include negative real numbers as coefficients. In fact, the claim that I have in the notes also works in that case. So I just want to point out that for any integer constant k greater or equal to 0, that this polynomial is big O of n to the k. This is also true for big theta as well. And I'm going to give you a quick sketch just to give you the idea. Now, remember what I did over there with the buckets. Remember, I tried to make everything on the left side at least what's on the right-hand side. So if I have a polynomial with all these coefficients, and each one of them has some power potentially being raised to it, I can use the same strategy that I did over there. I try to make what's on the left side, this would be this polynomial, make it look like this. But how do I do that? Well, remember, all of these n to the k terms, they're definitely, on their own, they're definitely going to be at least n to the k plus 1, and so on if you make the right choice of c. So just a general sketch. I'm just going to tell you what c and n0 need to be, but take a look in the proof. If I take the absolute value of the sum over from I is equal to 0 to k, so if I sum over all of these coefficients and I take the absolute value of them, in fact, if you really want to be nitpicky about this, you can literally just put that there. If you take the absolute value of each one, so it means, so if there's negative terms as the coefficient, so like -2 or -3, you can just take the absolute value that turns into a 2 or a 3 respectively. So if you just pick this particular c, you can pick n0 to be equal to 1. And the way I like to think about it is like light switches. So imagine each one of these like a light switch that you could toggle on or off. And that on or off is dependent on the coefficient. So remember, if it's 0, that means that that term doesn't exist. And what I would like to do is I would like to make what's on the left be the right. So I just look for all the ones with light switches that are on, meaning the coefficient isn't 0. And I simply could tell you, okay, well, if it's on, then I'm going to include it in this sum over here, which corresponds to just being a 0, right, in this sum. And all I do is I count up all the values of the coefficients. So all these are is just me taking the absolute value of each coefficient and adding them all together. So just in my example over there, what I did was I just made c is equal to 5 plus 1, because look, 5, 1, and of course there's a 0 here, so I can take the absolute value of all these and I get 6. Does everybody understand? So this is a standard trick you could use, and I give you the full proof in the notes. And if you use these two constants here, you could guarantee that it'll work for any polynomial that looks like this one. In fact, it's even true when it's just, like, it doesn't even have to be non-negative. It could, in fact, be negative as well. Just, of course, remember, we're assuming they're complexity functions, so the function can't be negative at any point. But anyways, are we okay with all this? So I just wanted to give you a general flavor of how to deal with polynomials. Are we all good with that? Okay, good. So now I want to proceed to doing a quick example. Also, it's worth noting, I do have another example in the notes of using this. So if this is really troubling you, don't worry. There is a full example where I take a much more tougher polynomial and I apply this theorem at you. So I'm going to do another example. Let me just migrate over here. Okay, so we're going to do an example with big omega. Now, remember, the only thing that differs in the definition of big omega is I flip this inequality like that. So the game plan has not changed. The only thing that's changed is this, that inequality. That's it. So I wanted to show you another example. We're going to show that log base 2 of n plus 2 is big omega of log base 2 of n squared. Now keep in mind the n squared's inside of the logarithmic term here. So I'm going to prove this for you. We're going to use the definition of big omega to do that. So what do? I describe what I'm going to, what my method is. I'm going to find c and n0 such that that holds for all n greater or equal to n0, right? So I'm going to say we find constants. That's supposed to say constants. We find constants c and n0 such that log base 2 of n plus 2 is greater than or equal to c times log base 2 of n for all n greater or equal to n0. So that's what we're going to do. We're going to try to figure out. Okay, so there's a question in the chat. Let me just grab my mouse, just because the chat window is not very big. Let me just take a peek. So you forgot to change. Ah, thank you. I knew there was going to be something I would have forgotten. Here you go. Let's change that O to an omega. There we go. There we go. Perfect. Thank you. So let's proceed with my example here. Now, I'm going to try to use a strategy that's kind of similar because I have something that looks like a log on this side and I have a log on this side, but I'm going to try to pick c so that I can account for this 2 here, but write something that is a little easier for me to follow through with. Now, this one, I admit, is going to be a little bit harder to see at first. Oftentimes, when you're doing these types of proofs, I recommend just first trying out some values and see if they work, and then write out the proof. Sometimes it takes a little bit of intuition to see what c and n0 should be or can be. Remember, your goal is just to find 2 of these. You're not trying to show me all of them. You just need to show me that they exist. So I'm going to try picking c is equal to 1/2. Then we find n0 so that for all n greater or equal to n0, log base 2 of n plus 2 is less than or equal to 1/2 log base 2 of n squared. Now, I want you to think back. I want you to think back about logarithms. Now, whoops, I want to have this inequality go the other way, right? Like that. Don't forget that. That's important. I like to do these things intentionally just to throw you off. Okay. Anyways, I have this on this side. I want to show that this is greater or equal to that. And there's a property. So you're going to see why I'm going to pick c is equal to 1/2 in a moment. I want you to look at log base 2 of n squared. Now there's a very special property that exists for logarithms. Does anybody see anything I could do with log base 2 of n squared like this? There's a special property. There's a property of logarithms I could use to get rid of this exponent right here. So I could do something else with it. So put the 2 out in front. So you could use, it's called the power, it's like the power property or power rule of logarithms. So observe, so here's where I'm going to make an observation. Observe by the power rule of logarithms, that 1/2 log base 2 of n squared is equal to 1/2 times 2 times log base 2 of n, which is, of course, remember there's a half here multiplied by a 2. That is, in fact, that's just 1, right? That just becomes 1, which is, in fact, equal to log base 2 of n. So this is where it gets neat, right? So now I have something on the right-hand side that looks like log n. But what's on the left-hand side of the inequality? There's log n plus a little something, right? So I pretty much have everything in the bag at this stage. I just need to put it all together. So all I need to do is notice that for all n greater or equal to 1, I'm just going to pick the smallest value of 1. That will work. But I must warn you, when you're dealing with logarithms, you have to be careful because, remember, n is inside of that logarithmic term. So sometimes you might need to pick a larger n so that you create terms on one side of the inequality so that you could kind of use a product rule of logarithms to split them apart and argue that, oh yeah, well look, one of these terms, like maybe like 4 or something, like if I had log base 2 of 4, for example, that example would be that's equal to 2, right? And there's a special property that logarithms have, like many of the functions we use in this class. They're increasing functions. So that means if I put in n and n is equal to 4, I know that if I put n is equal to 5, you know it's going to be no less than log base 2 of 4. So sometimes these things pop up. I know it will pop up probably on the assignment. So that's why I'm mentioning it. So if I have this, then I could just simply write, okay, well, log base 2 of n plus 2 is greater or equal to log base 2 of n. So choose n0 is equal to 1. So now I have choices for c and n0. Therefore, and now I just tie everything together. Therefore, by the definition of big omega, log base 2 of n plus 2 is big omega of log base 2 of n. N squared, sorry, n squared. And we're done. Bam. Is that neat? So sometimes you'll see that the ideas I use tend to really rely on me trying to make something that looks like on this side. I want to make sure that whatever's on this side is going to be bigger or equal to whatever's over here. And I use properties of this over here to try to make it or massage it so it looks kind of like this, if I can. So is this example all right? Did everybody follow it perfectly fine? So I'm going to do another example, but it's going to be big theta. Okay, I think we're perfect. So let me erase this. We're going to do an example of big theta. Now, of course, if you remember back to when I defined big theta for you, you'd recall that it's simply that it's big, has both the property that if I have f is big theta of g, then it means that f is big O of g, and also big omega of g, right? So if I have big theta, this time I remembered it. Thank you. So if and only f that's how we know it's in big theta, is we know that both of these hold over here on this side. Now, what I'm going to do, now, you of course could prove these separately, and that's perfectly fine. Like, for example, on the assignment, if you want to be like, oh, okay, I'm just going to prove big O. First of all, I'll have like a big O part where I'll prove that f is big O of g. And then you'll have the omega part where you say, okay, this is f is big omega of g. And then you say, therefore, because it's this and this, therefore it's big theta of g. That's perfectly fine. I'm going to show you an alternate way where I'm going to try proving both of these at the exact same time. But you have to be a bit careful when you do this. So I'm going to prove that 3n cubed plus 5 is big theta of n cubed. Remember, like I said, you could do the big O and big omega separately. Sometimes that's helpful if it's a little bit more complicated. Other times you'll find that the C's tend to be very closely linked to one another, and it kind of wastes a lot of space when you try to write this out. So this is one of those examples. So to prove the claim, remember, I got to write down the game plan. To prove the claim. Now, I'm going to rip apart these two definitions here. Now, remember, in this definition, it says I need to find a positive real constant and n0, such that f of n is less or equal to c times g of n, right? In this one, I need to find a constant. We'll call it, say, c2, for example. And we also need another constant, and another n0. We could call it maybe n1. But I'm just going to amalgamate that n0 into one constant, because if my inequality works for one of them, then it surely should work for the other. Or if I want to make sure that both work, they better be the same constant. But keep in mind, you can do it separately with two separate constants. But remember, in this case, all I'm going to do is I'm just going to rip apart these two definitions and just tell you what they mean. So to prove the claim, we find constants. So all I'm doing is I'm invoking the definitions of both of these, and I'm just going to simplify it down a little bit. We find constants, C1 and C2, which are positive real constants, and n0. Like I said, if you want to have n1 and n2 like right here, you would just have to compute the maximum of these two constants if you want to play around them like a single constant. But you don't have to do that. You could just have two separate constants, n1 and n2, or whatever you want to call them. I'm just making this a little slicker. That's why I want to show you this, because otherwise I would just show you more big O and big omega examples. Such that, now this is where the tricky part comes in, such that for all n greater or equal to n0, C1 times n cubed is less than or equal to 3n cubed plus 5, which is less than or equal to C2 times n cubed. So all I've done is I've sandwiched f in between g, but with respect to, this is the part with the big omega part, this is the big O part. Does everybody see that? So I need because remember, if I find an n0 that works for this entire inequality, then it works regardless if you're looking at this part or that part. It doesn't necessarily have to be the smallest possible one, as long as it works for this entire chain of inequalities. So what I'm going to do is I'm just going to invoke the same trick I did before. So remember the buckets. Remember, if I have 3n cubed and a 5, I have an n cubed here and an n cubed there. What I would like to do is I would like to make something that looks like this on this side and that side. Can somebody tell me what would be kind of nice constants I can pick for each one? So I'm hearing a 4. I'm hearing a 4. So I hear one that I really like in the chat. I like 3 for this one. 3 could work really well here. Now, you could go with 4, but you would have to be really careful with this because now you have this plus that, and then now you have to like figure out an n over here that will work really nice there. Think back to what I did with the polynomial trick. This is one coefficient, that's another coefficient. If I add these two coefficients, I get 8. So what I'm suggesting is that we maybe pick C1, maybe to be 3, because you agree with me that if I can make this 3n cubed, that's 3n cubed plus 5 on this side, right? But I know that the whole idea is that with this bucketing approach, that if I make this 8, you'll know that 3n cubed is indeed less than or equal to 3n cubed, and 5 has to be less than or equal to 5n cubed, right? For all n greater or equal to 1. So that's why I'm going to decide these two constants here. But you could try other ones. You'll just find that you may have to pick a different selection for n0. Like I said, there's many constants that could work. I encourage you to try them. So I'm just picking ones that are very easy to argue. So I don't have to pull out root solving or anything of that sort. Pick constants. C1 is equal to 3 and C2 is equal to 8. Then we find n0 so that for all n greater or equal to n0, we have 3n cubed. 3n cubed is less than or equal to 3n cubed plus 5, which is less than or equal to 8n cubed. Like this. So this is my game plan. So what I'm going to do is I'm going to look at each side of the inequality, like this part, and then that part. Now, it shouldn't be very hard for you to see that 3n cubed is less than or equal to 3n cubed when I add 5 to it, right? You guys won't be too anal if I decided to just say this is just true, right? For all n is greater or equal to 1. That's something I think computer scientist students would really, really think, like, ah, that seems kind of compelling. I just add 5 to the one side, so it seems pretty easy. So I'm going to say first, on the left-hand side of the inequalities. So when I say this, I'm talking about this right here. I have another way of phrasing it in the notes, just I'm trying to keep things on time. So left-hand side of the inequalities, notice that 3n cubed is less than or equal to 3n cubed plus 5 for all n greater or equal to 1. So that part's done. Now, second, on the rightmost inequality, on the rightmost inequality, 3n cubed plus 5 is less than or equal to 3n cubed plus 5n cubed, which of course this is equal to 8n cubed, which is what I have right here, which is equal to 8n cubed, as 3n cubed is less than or equal to 3n cubed for all n greater or equal to 1. And 5 is less than or equal to 5n cubed for all n greater or equal to 1. So I'm going to just simply choose n0 is equal to 1. Therefore, by the definition of big theta, 3n cubed plus 5 is big theta of n cubed. And we're done. So does everybody see how I did this? I essentially structured everything so that I can isolate out these two constants on each side. Then I just show, I look at this part of this chain, then I look at that part of the chain. Then I just use the same tricks I did before. It's just a big bag of tricks, isn't it? So the next thing I want to do, I'm just going to shift gears. So hopefully everybody's fine with this. I'm going to proceed to doing an example that's a little different. I have another way of doing it in the notes. So if you're familiar, for example, with proof via contradiction, there is a way of doing that as well for this, but I'm just going to keep it to the bare basics here, just to keep everything flowing so that we can keep everything on track. I showed you how you could prove is claims. So like F is big O of G, F is big omega G. I want to show you an example where I show that F is not of a something. So I want to remind you that if I give you F, and I want to say F is not big O of G, I want you to think about this. The definition of big O says that there exist two constants, C and N0, such that for all n greater or equal to N0, the inequality F of n less than or equal to C times G of n holds. So what I would like to do is I would like to negate that definition. So that means I have to negate the rules for which I need to prove the claim. So if I want to have this, believe it or not, is no different than if I were to write the following. So remember, when I say it's not of that thing, that means regardless of what constants I could select, there has to exist some n so that the inequality that I originally posited has to fail. So it means that there can't exist those two constants. That's what it means when it says it's not n. Those two constants can't exist. So I'm just going to write that out a little bit more formally here. So I'm saying if and only if for all C, which are positive reals, and N0, which is a positive integer, there exists n greater or equal to N0 such that, and I'm just going to flip the logic of the inequality, such that F of n is strictly bigger than C times G of n. And keep in mind, you can do the same kind of trick with omega and theta. It's just, all I'm doing is I'm negating the logic of the statement. So some of you may be familiar with that technique, some may not be, but that's okay. This is the negation of big O here, and we're going to use this for an example. So what I'm going to do is I'm going to show that n squared over 4 is not big O of n. Now, you could quite look at this and be like, okay, well, there's an n squared on one side and there's an n. So I'm going to try to take advantage of that fact to derive an inequality for which I can never find a C or an N0 that would work. In fact, if I find any C, it would invalidate the whole thing. So that's sort of what the game plan is. I'm going to assume that somebody gives me some arbitrary C and N0, and I'm going to show you how you could show that the inequality doesn't work. As in this. Is everybody clear about that? So I'm going to proceed, and hopefully we'll be all right with this. So I'm going to let C and N0 be arbitrarily chosen and fixed. So if you're wondering what that phrase means, it just simply means as it suggests. I imagine C and N0 just sitting out here, just like if they're in the lake and the C's or N0s are fish in the lake. I pluck out two fish and I put them on the table. That's what I mean by arbitrarily chosen and fixed. I just take any one of those two and I put them down and I say, I fixed you down. That's what the phrase means. So anything I say has to work for any C and N0 that I pull out of the lake, just like fish. So what's the goal? If we want to prove this directly, I need to find the n now. So notice I have to find n. That's why it says there exists n greater or equal to n0 such that this inequality holds. That's all I have to do. So I have to assume arbitrary c and arbitrary n0. I got to find n. That's the only thing I have to do. We need to find, so I'm just doing the same thing I was doing before, except we need to find n greater or equal to n0 such that n squared over 4 is greater than c times n. Now, all I'm going to do is I'm going to divide both sides of this inequality by n. So I'm going to say, notice that n squared over 4 is greater than c times n, if and only if. So if you really wanted to really know what the if and only if means, just divide. You could write by dividing both sides of the inequality, we see that. But I'm just going to use if and only if. N over 4 is greater than c. So I'm going to multiply both sides of this inequality by 4, implying n is greater than 4 times c after multiplying both sides by 4. So now this is where I'm going to pick n. So all I'm going to do is now pick n. Now notice that I have an inequality right here. All I need to do is pick it so that both this is going to be bigger than or equal to n0, and it's also going to be bigger than anything I can get on this side. So if I do that, then I have found the n that will work for this, right? That's all I'm going to do. So I just massage the inequality, and then I just simply try to figure out a c and an n0. So you're going to find that these proofs always typically are written in a way that they have n0 and c appear in the selection of n. Because remember, like I said, they're arbitrary. So here I'm going to go, so pick n is equal to the maximum. So I'm going to take the maximum of two values. I'm going to take the maximum of n0 and the ceiling. Now, if you don't know what the ceiling means, these two brackets that go like this, that means round up to the next integer. So if this isn't an integer, 4c is an integer, it just rounds up. Like if I have 4.5, the ceiling of 4.5 is 5. Just like there's also a thing called the floor. The floor of 4.5 would be 4. That means round down. So I'm going to pick n to be just slightly bigger so that this inequality will work. And if you notice that, I could say the following. Then we have n greater or equal to n0. And for this value, and this value n, the inequality is satisfied. The inequality is satisfied. Therefore, now I have to put this all together. Therefore, n squared over 4 is not big O of n. And we're done. So notice all I did is I just have a different game plan. I use this negated version of the definition of big O. It tells me I have to find some n, but it has to work regardless of what c and n0 are. Is that clear, everybody? So in the notes, I've included another example where I use contradiction as opposed to a direct negation proof like this. So also in the notes, I've also included properties of asymptotic notations. I would like you to read that section for next time. What I'm going to do is I'm going to maybe do 1 or 2 examples from there. I'm just going to summarize what's there. And but please read that section because I'm only going to highlight a couple of examples from there, but I'm going to kind of run through the properties I have there. And then we're going to move on to a new topic. So anyways, with that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.